muons, again, we'll just do beta. Beta of the muons is 0.997528. And, well, that might be it. From the muon's point of view, how fast are the muons going from the muon's point of view?
0.
Okay. Oh, no units for beta. Well, the distance that they travel was
It was the
1624.
yeah.
From the muon's point of view, how far did they travel?
The same. Or also 0.
Sorry?
Also 0.
Also 0.
Okay.
Muons aren't moving. But from the muon's point of view, so delta x, we should put down muons, 0 meters. From the muon's point of view, what is traveling?
The other stuff. Everything like the car, being in a car window scenario, like everything else is moving by you. I guess.
So in this particular scenario, if the muons aren't moving from their point of view, something is moving though.
The Earth
Yeah. How fast is the Earth moving?
at speed.
Yes. I assume you're pointing at that one right there.
Yes.
So they at least agree on something. They both agree on the speed. They just disagree about what's moving at that speed. What is the chances? All right, so delta x Earth is 0 meters. Actually, we're doing beta right now. Beta of Earth is 0. Beta of Earth is 0.997528. So from the muon's point of view, the Earth is coming, zooming right at them. How far does the Earth travel?
Also 0.
If you're seeing the Earth zooming right at you, you're saying the Earth's not moving?
Why are we talking about from which respect?
Muon's, valid question. If I didn't say it explicitly, you're supposed to read my mind on that. From the muon's point of view, how far does the Earth travel?
Whatever distance that we have is 1624.
It will not be 1624. If the Earth is traveling at them at this speed right here, for
Oh, we know the time, right?
yeah, we know time. So the time that the Earth is moving is
So that's somewhere.
0.381 microseconds.
So we can find the distance.
Here, the time that the muons are traveling is was it 5.43? Yeah, 5.43 microseconds.
.8 times 10 to the negative 7. I think it's something wrong. So is
Yeah, something's wrong there.
the 0.997528
Right?
times 0.381 times 10 to the negative 6.
Times, don't forget, this is the proportion of the speed of light. So times 3 times 10 to the 8th speed of light.
Yeah.
What is the equation you're doing right now?
3 times 10 to the 8th.
3 times 10 to the 8th.
Yeah, okay, it's 114.0174504.
No doubt, all significant. You want some units in there?
Meters.
All right, the formula he was doing was speed times time. The complication is that's not a speed directly. It directly relates to speed, but that's not a speed. That is a fraction of the speed of light.
So you do that times the speed of light.
Yes.
That's 3 times 10 feet. And then
Approximately.
Then you multiply that number by
The time.
Okay.
Okay, so there's this big disagreement about, well, actually, they both agree that something's moving at almost the speed of light. They disagree on what's moving, they disagree on how far that object moves. So what is the ratio of the distance that the Earthlings say versus the muonlings?
Quite a lot.
So if we did delta x that the muons say from the Earth's point of view over the distance that the Earth travels from the muon's point of view, that'd be 1624 over 114.174504.
I got 14.22, but I didn't use all the decimals.
Okay.
422.
Which is pretty darn close to our value of gamma. I'd say there's a rounding difference there. So we have another relationship here that actually works, and we could do a more formal derivation, but it's very important. So we had T is equal to gamma TP. And now we have a length, or a distance, we'll just do length, is equal to gamma times the length. But what is the proper distance? Is the proper distance what the muons are seeing, or is the proper distance what the Earth is seeing?
Is it the average? Or like
No, it's not the average.
It's neither. There is no proper distance.
No.
Yeah.
It's not the Zen answer of what cow. That goes to a story in high school. The teacher read a Zen story to us and asked what the cow represented in the story. And we all came up with answers, and he said, all of you missed it. The question is, what cow? So anyway. Let's think about the distance. The distance that Earth says, the 1624, is that distance measured sort of at rest from the scientist's point of view? You have this elevation here, you have this distance down here. Is that those measurements, are those at rest relative to the scientist?
Yes.
Okay. The distance that the Earth moves, the 114 meters, is that distance from the muon's rest frame? I mean, is this at rest? Is the Earth at rest relative to the muons?
No.
No, because this is the distance that the muons say the Earth is traveling. The Earth is zipping right towards them. They are not moving. They are not both at rest together. Whereas this is at rest. So the proper length is going to be from the Earth's point of view.
Okay, makes sense.
You can usually think through, you're going to end up with a gamma in there somewhere in a lot of these problems. And then you just think through, all right, which one's got to be the bigger one? Okay. We'll do the math so that the bigger one comes out to be bigger. This is known as time dilation. And this is known as length contraction. I don't know why it's not called length dilation, but it's not. Length contraction. A similar experiment was conducted in 1962, the, of course, Frisch and Smith experiment, and they came out with the same conclusion: relativity works. So those are the two big experiments, and then there's one more experiment which brought in general relativity. Any questions before I do a brief bit on general relativity, which should harken back to something that we did last semester? But any questions on this?
So is that just to derive those formulas? To like make sure that it's right? Or to make sure this need a...
This was the experiment that showed that special relativity has some merit.
Okay.
It's not Dr. Fox propaganda.
You know, there's still the dream of being able to go an entire class making everything up. But I don't want to face the reality of if no one asks a question or challenges it, then I'd go, this was all fun. Why did you believe any of it? All right, general relativity. I will give almost the entire extent of my knowledge of general relativity. If the thought experiment is a person is in a box, cannot see outside, standing on a scale, and the scale reads whatever his weight is. Is there any experiment that can be done? Well, the answer is no, but is there any experiment that can be done to differentiate between there's a planet here, and he is in this box on a planet with an acceleration due to gravity of g, or he is in space and the thing is accelerating at that same rate? Is there any way to tell the difference? And the answer is no. There's no way to tell the difference between these two. If I shoot a light, across here because it's accelerating, if there's no acceleration, the beam's going to go straight across. But if I'm accelerating, the light's going to hit below where it started. It's going to curve down, just because where the target was is now moved faster than it was when it came out. So if there's no experiment that can tell the difference between these two, and this laser light would curve, well, it should curve over here too. So the general relativity is this idea of that there's something about mass itself, that the mass of the planet would cause things to curve. The first evidence that this had any bearing whatsoever happened in 1919. You have, it was done during a solar eclipse. Yep. Presumably drawn to scale. You're standing right here, light gets blocked out, so you actually have an opportunity to see things that are sort of just off the sun. And what general relativity predicts is that if I've got some object over here, that its light rays would come along, they would bend around the huge mass of the sun and come there as well as from there, and you would see a double image of it. Actually, if you were just perfectly lined up, you would see a ring. And there are some really incredible pictures that have been taken of this ring of mass because it's bending around something. But Eddington was the physicist, and he saw this multiple image of the same object, thereby giving evidence of general relativity. Thus the story on the trip back, he was talking to reporters, and they said, I understand there are only 3 people in the world who understand general relativity. And Eddington said, oh, who's the third? The arrogance of physicists. At least he acknowledged that Einstein understood it. Now, if you take this into account, that if mass causes a warping of space, it also, and there's a big leap here, but there's also a warping of time. So if I were in a plane and I was traveling around the world, there should be a difference between the time on the ground and the time in the plane. The time in the plane will vary because of special relativity, because it is traveling at some speed relative to the Earth, as well as some general relativity would cause some warping of time. So they ran this experiment in 1972, and they ended up with, indeed, evidence. Let's see if I actually have the numbers here. There we go. And there was a difference if you traveled east or west. They basically put an they had two atomic clocks that were synchronized to the nanoseconds. Yeah, to the nanoseconds. And they put one into a jet, flew it around the world, and then compared the two clocks. The clocks were off. The prediction for the eastward journey was the one on the plane would be off by -40 plus or minus 23 nanoseconds. So this was predicted. And the experimental was -59 plus or minus 10 nanoseconds. So definitely within the same range. And then the westward journey was even better. The prediction was 275 plus or minus 21 nanoseconds. And the difference was 273 plus or minus 7 nanoseconds.
Why is it so much more the second time?
With the first case?
No, the second case. Can you explain that again? Like, why is that two?
Oh, I don't know.
Okay.
Yeah, general relativity kicked my butt. Yeah, that's something I will never get back. It's on my bucket list to understand that, but I don't. Sorry, flashbacks. I would like to think that that professor has learned how to teach since then. But
Random question. Did you plan to do this on the day of an eclipse, or is that just chance?
it just chance. No, I've had this plan since, since the last one,
17 years.
something like that.
It's actually in 77. I watched this fascinating video on like the whole like how unique each eclipse is, especially how unique this one is, because of like there's like 3 or so factors about like, because there's like multiple times throughout the year, so many times actually, each day almost, to where they line up the sun, the moon, and the earth from looking down. But looking at it from looking at it from another perspective, the moon is always at a angle, like just above the sun and the earth, and that's when you can see the moon in the daytime.
Mm-hmm.
So, but then there's these lunar nodes to where it's close enough down to where it's at the same level of the earth. So this is something that you have to take into account. But then the orbit of the moon itself slowly shifts as well. So it's like so many factors that take into account until there's an eclipse, because there's you have to balance out all of these different angles, and they're constantly changing, and I was like, what? So you have to, so essentially each year, it'll be each year, because it's 177 some days between each solar or lunar solar eclipse. So I sat down and I watched that same video for like four or five times. Still only understood half of it. Yeah,
That's physics.
that's physics.
All right. All this is well and good. However, here's a problem. There's a resolution to it. So, Earth, planet X. A rocket ship shoots off to planet X and then returns. we'll have it traveling 0.99 times the speed of light. If the rocket ship is gone for a year, from the rocket's point of view, so the astronauts will age 1 year. So that is the time for the astronauts. How much time passed on Earth? Well, we can just do, first off, let's figure out what gamma is, the Lorentz factor, so 1 over the square root of 1 minus 0.99 squared. Astronauts, is that the word you're trying to figure out?
The other side of the equation.
1 year.
7.08.
So the amount of time that passes on Earth would be 7.08 years. Conveniently, 7.08 times 1.
Why?
Because that's equal to gamma times the proper time. Proper time is 1 year.
I see.
Yeah.
Okay.
Alright. That's stuff that we've sort of covered already. Whether you want to believe it or not, that's up to you, but this is to be borne out by the experiments. Here's the problem though. As people are trying to pick this apart, let's flip points of view. Let's say that from the point of view, see that was the point of view of Earth as the rocket goes and comes back. From the point of view of the rocket ship, Earth zips away, as well as Planet X. And then they both turn around. So we can just flip the points of view, and shouldn't it be different that the people on Earth age a year, and the people on the rocket ship age 7.08 years?
No.
Which point of view is correct?
You said the bigger one. Well, you said let the bigger